Hello everyone. So here I'm going to show you one example of liver segmentations for CT using one structure from deep learning, which is called BigMedic, as is shown in this image. And then we're going to show these segmentations apply to the clinical context. As you can see here, this structure has three channels, the high resolution channel and the lower resolution channel. Here, the input image is downsampled by 1, 5, and 15, and then small patches are extracted from these downsampled images. The first channel is the high resolution channel, which actually use the input segment from the images, the input patches, which is sampled from the images with the original resolution, and then it actually extract the high level features. And then for the second and third channel, which use the input patches sampled from the downsampled images, and they extract the lower level and high level features. And then through fully connected layers, we combine these features together to and then through the classification layers, we output a probability map where each voxel represents the probability of one voxel belonging to liver or non-liver. Then through cost function, here we use binary cross entropy. We combine the similarity between the ground truth and the probability map. And then we use optimizer to uplift weights so that we can minimize the cost function. Then through many times of these kind of iterations, we stop it until the binary cross entropy value is small enough. And then here our model is trained on 242 training datasets with 101 datasets from LEADS challenge, 111 datasets from medical segmentation decathlon challenge, and 18 from liver challenge, and 12 from third datasets from a hospital. And then we validate them on 25 datasets, 10 from LEADS challenge, 2 from liver challenge, and 13 from our hospital. After that, we test the model on 40 third datasets from our hospital. Now we go to our experiments. So basically, we after we acquire these CNN segmentations, we ask a radiographer to manually adjust these CNN segmentations from the 40 third datasets, and then we compare the CNN segmentations, manual segmentations from the radiographer, and the manual adjustments of thin segmentations from the expert. After that, we randomly select out 20 datasets and ask a nuclear medicine physician to manually adjust these segmentations. Then by comparing the variability between the manual segmentations from two experts and the manual adjustments, we can see if thin segmentations can help decrease the inter-observer variability of segmentations. And also for these CNN segmentations, we give a score to them. If the score is smaller than 3, we think that a very large amount of adjustment is needed. It's better to segment the liver manually from scratch. If the score is no less than 3 and smaller than 4, we think that the adjustment is needed, but after adjustment, the liver segmentation can be used for clinical use. If the score is no less than 4, we think the CNN segmentation liver is quite good and only very slight adjustment is needed. Here we evaluate our segmentations by using 4 metrics. The first one is called dice similarity coefficient. As you can see in the first image on the right side, the more overlap the two segmentations have, the larger the dice coefficient is, and the value is always between 0 and 1. And the second metric is called volume ratio, which is equal to volume 1 divided by volume 2. And the third one is called mean surface distance. As you can see in the second image here, we have 2 contours. For each point on contour X, we find its closest point on contour Y and form a subset of distances. Similarly, for each point on contour Y, we find its we'll find this closest point on control X and then form another subset. Mean surface distance is actually the mean value of two subsets of distances. The Hausdorff distance is the maximum value of two subsets of distances, which actually measure the worst case in two contours. Firstly, we show the results from the 23rd datasets. In this box below, you can see the CN segmentations, manual segmentations, and adjusted CN segmentations from our radiographer. And you see that the adjusted CN segmentations actually agrees more with the CN segmentations than the manual segmentations. And then we show the score given to these 4D segmentations. You can see that 16 segmentations are quite good and only needs very slight adjustment. And 19 segmentations need some adjustment, but after adjustment, they're good used for clinical. After that, we show the comparison of the agreement between the manual expert delineations and between the two manually adjusted segmentations from the 23rd datasets. You can see that the agreement between the adjusted CN segmentations are actually much larger than the agreement between the manual segmentations. This actually shows that the CN segmentations can help decrease the inter-observer variability. So basically, this is the all things about our example for CN segmentation for CT images.